given a rational function and a square root function. Let's look at how we can evaluate a composition and then also find the domain. So here we're finding g of f of p. So our function f of p is equal to the square root of p plus 2. So we're going to take that and that's going to become the input into our function g. So we're going to do g of the square root of p plus 2. So our function f is getting plugged into our function g. So in our function g, where we had a p before, we now want to replace that p with the entire expression, the square root of p plus 2. So we're going to have 1 over the square root of p plus 2 minus 3. So we could go ahead and combine the like terms in the denominator and write this as 1 over the square root of p minus 1. So this is our function after doing our composition. Now let's think about the domain of this new function that we have created. When we're thinking about the domain of a composite function, we need to think about two things. The domain at the start, what was our initial function, and also the domain at the end, and then we'll combine those two statements. So let's think about our domain of what we could call the start. So this is the function that we started with. We started with the function f of p. So f of p is equal to the square root of p plus 2. Now when you're thinking about the domain of a square root function, we focus in just on what's on the inside of the square root. You can ignore the plus 2, that doesn't affect the domain, and we just need to make sure that p is greater than or equal to 0. So our initial function, or our starting function, was the inside function f. Our function f says because of that square root, p needs to be greater than or equal to 0. Now let's think about where we were at the end. So our ending function is what we had after we did our composition, our g of f of p. So that was 1 over the square root of p minus 1. So this is a rational function. When we have a rational function, we want to look just at our denominator. We want to make sure that the denominator is not equal to 0. So the square root of p minus 1 cannot be 0, or we'd have a division by 0 problem. So adding 1, this means that the square root of p cannot be equal to 1, and if that's the case, p cannot be 1. So we now need to take these two statements, p is greater than or equal to 0 and p is not equal to 1, and think about putting those together. So you could even picture this on a number line. So p cannot be equal to 1. So you could think of that like an open circle on your graph, and p needs to be greater than or equal to 0. So it can be equal to 0 or greater than 0. So we need to make both of those statements true at the same time. So we have all of those things that are greater than or equal to 0 except for 1. So if we were to write this in interval notation, it would go from 0 to 1, a bracket with the 0 and a parenthesis with the 1, and then from 1 to infinity. That this is the domain of our composite function, g of f of p. The restriction that p is greater than or equal to 0 comes because the initial function, or the first place you would evaluate, would be our function f. And because of that square root of p, we need to make sure that we only plug in positive values. And then we need to make sure, because of our ending function, that p is not equal to 1. If you think about if you tried to evaluate g of f of 1, f of 1 we could do, square root of 1 plus 2 is 3. But then when you plugged that 3 in, 1 over 3 minus 3, you'd run into division by 0. Let's look at these same two functions, but now let's switch and think about f of g of p instead. So this time our starting function is g of p, that 1 over p minus 3. So we need to take that and plug it into our function f. So our function g is going into our function f. So this is going to become the square root of 1 over p minus 3 plus 2. For us, we're just going to leave it in this form and not worry about any kind of simplifying from there. So now, let's think domain. So the domain for our starting function g of p is 1 over p minus 3. So when we have a rational function, when we have a denominator, we need to make sure that p minus 3 is not equal to 0, which means that p cannot be equal to 3. So division by 0 is what we're trying to avoid when we think about a rational function. If we think about our function that we have at the end, this is our composite function, f of g of p. So this is the square root of 1 over p minus 3 plus 2. With a radical function, we look at what's on the inside of the radical, and we want to make sure whatever's on the inside is not negative. So in this case, that means that 1 over p minus 3 needs to be greater than or equal to 0. We haven't yet looked at how to solve a rational inequality like this, so just think about plugging in some numbers. If you were to plug in p equals 2 or p equals 4, which one of those gives us a true statement? So we can't plug in p equals 3, that leads to division by 0. But if you plugged in p equals 2, 1 over 2 minus 3, 1 over negative 1 would be negative 1. That is not greater than or equal to 0. But if you were to plug in 4, 1 over 4 minus 3, 1 over 1 is 1, that is greater than or equal to 0. So the values of p that give us a true statement are all going to be those p values that are greater than 3. So 4 gives us a true statement, 5 would give us a true statement, 6, 7, and so on from there. So if we put these two statements together, p cannot be equal to 3, and p does need to be greater than 3. Putting those together, the domain for our composite function would go from 3 to infinity, a parenthesis at 3 to show that that cannot be included, and then anything greater than 3.